Through more than 100 years of existence, cinematography has developed a wide range of techniques to track actors in motion. Though the possibilities are close to infinite, traditions and conventions have shaped a common sense and a language of how such scenes should be shot. The questions we address in this paper are twofold. Is it possible to extract the camera techniques used in these film clips and hence characterize the motion of the camera in relation to the motion of the characters? In essence, extracting a camera behavior from a film clip. And is it therefore possible to retarget a behavior extracted from a movie into a 3D animation? In this paper, we propose a technique that takes as input a single or sequence of reference clips with at least 2 characters, extracts the camera behaviors it is composed of, then, given a 3D animation, is able to compute a camera path which reproduces the extracted camera behavior. Our approach is driven by examples, does not require prior labeling of datasets, and is controllable. Our system works as follows. We first design a cinematic feature estimator using a deep learning network, which is capable of automatically extracting high-level cinematic features from images, such as camera angles, 3D distances, layout of characters, and relative character configurations. Then, temporal sequences of cinematic features can be fed into a gating network, which is able to recognize the behaviors of the camera in a latent space representation, the camera behavior space. Finally, given a trajectory in the behavior space, we use a prediction network to compute the sequence of camera poses given a known 3D character animation. First, we validate the results of our cinematic feature estimator. We analyze a film clip to extract 2D skeletons. We then rely on our trained deep learning network to estimate cinematic features such as camera angles, composition, and character relative configurations. We then design a 3D animation that only reproduces the character layout of the film clip, and we directly apply the camera parameters estimated by the network. As displayed in the side-by-side comparison, the camera angles, framing, and distance appear similar to those of the reference on a frame-by-frame basis, meaning that the features are well estimated. Naturally, if the 3D character layout is significantly different from the real sequence, the camera motion would be different. Hence, we need to learn to which character layouts should some camera motions be applied.
Yeah. How do you know I'll come back?
Look. Frank, nobody's chasing you.
We now perform a validation of our gating plus prediction network. We start by selecting a synthetic reference clip and use the gating network to estimate the camera behavior within our camera behavior space. We use this camera behavior to compute a new camera motion on the same 3D animation. We feed the prediction network with character features from the animation, and the prediction network computes the camera path corresponding to the selected behavior. As you can observe, both camera motions are similar. In the second stage of validation, we use the same extracted behavior to select, among all real movie clips from the test data, the one which is the closest in the camera behavior space. We then use the selected clip and apply its behavior to the same 3D animation. As displayed, the clock representations of the camera behavior space appear similar. Finally, we compare the sequences generated from the real and the synthetic movies. The similarity in behaviors demonstrates the capacity of our system to both estimate behaviors from clips and generate camera motions that enforce the selected behaviors. We first present results on a heated dialogue scene.
Did you hear, Jim? Liza's...
Yeah, I know.
This is great, Jim. She's gonna make
Please.
it. Dr. Blum
Anne,
says she won't have
just
any...
stop!
Why are you acting like this? What is it? Look, Jim, we need to communicate. You do realize we're having a child, right?
You honestly didn't suspect anything? There was no car accident, Anne! They were assaulted, but the whole thing was swept under the rug. But it really happened.
You mean the 5, the ones
No,
who found?
you're not listening to me.
They don't exist, Jim. You told me that yourself. Look, you need some help. You really need to see someone.
Was that what Melanie said? That I'm having a nervous breakdown? That this has all happened before? Jesus, dude, wake up! She bought me off just like you and like everybody else! Do you get that?
Don't touch me!
Anne,
Don't come any closer.
We then present results on a fighting scene. By using different reference clips as inputs, results demonstrate both the range of camera motions that can be created and the visual quality of the computed motions. We compare our results with a state-of-the-art optimization-based approach called Camera on Rails, which automatically generates the camera trajectory in between two user-specified end frames. Here we further optimize the path by varying the number of keyframes to be inserted so as to get close enough to the reference path. Optimization-based method generates smooth camera trajectory in between two user-specified end frames. However, it cannot guarantee C1 continuity between adjacent sub-trajectories, which will cause jittering artifact illustrated in the video. The smoothed and raw camera trajectories are demonstrated side by side. Fast camera shake caused by characters' random vibration can be effectively smoothed out by a sliding averaging window. Thanks very much.